Okay, so this is a re-recording of the Module 1, Lecture 1 for Organic Chemistry, CHE 255 at the University of Southern Mississippi for the fall 2024 semester. So there will be this template slide interspersed throughout the slide decks where we'll pause class and ask and answer questions. And what you'll notice about this slide is there is this hexagonal template which you can use to help draw structures. So for example, many of the structures that you'll draw will want to conform to specific bond angles, and that's based on the hybridization of the carbon involved. So this is just provided so that you can draw some clean structures, and we'll talk more about hybridization and bonding in Module 1. So what is organic chemistry and why do I think it's important? On this slide, there is a molecule called zidovudine. And let me give you the bigger picture here. So this molecule is prescribed to people that have HIV or AIDS, and it helps them live healthier, productive, and longer lives. So as you can see in the molecule, there's a hydrogen, oxygen, nitrogen, but what you don't see explicitly drawn are carbon, so there's no C drawn. And so why is that? And we'll talk about that in the first lecture, also throughout Module 1. But so the molecule is a collection of atoms with bonds and specific patterns that give it this therapeutic indication of helping people with HIV and AIDS. So organic chemistry is directly tied to society through helping human health amongst other areas. And these things are made by pharmaceutical companies, so that impacts the economy. There's a lot of talk about the cost of prescription drugs. Why do they cost so much? This sort of thing. So I believe the course really from the atomic level to the societal level is important. And we'll talk about in Module 1 periodic trends, so electron configurations, how electrons go into orbitals. Electronegativity is going to be a really big explaining factor in a lot of the trends that we see. So one thing that might be different in organic chemistry versus general chemistry is how do atomic orbitals, how do we use them to explain functional groups? A functional group is a discrete set of elements and bonding patterns within a molecule. And we have to use the atomic orbitals to form molecular orbitals. And that requires hybridization, which is a mathematical concept. We'll talk very qualitatively about these things, but really what we're trying to do is keep track of electrons. Functional groups impact physical properties of the molecule, and ultimately the orbitals, functional groups, give it its three-dimensional structure. And so we can see here in this space-filling way of communicating AZT, no one depiction of a molecule is exactly accurate, really. I mean, these are just visual tools that we're looking at to understand, what properties the molecule has. So we have to draw things like this, obviously. The 3D space-filling molecule gives you maybe a better representation because, each atom has a van der Waals radii that needs to be considered, but so this does indicate shape. The molecule with different bonding patterns and elements has a shape. And how do we know what a molecule is? How do we know what elements are there and how they're bonded to one another? And so another concept we'll use is spectroscopy, the interaction of light with matter. And Organic 1 will focus on three main forms: infrared spectroscopy, nuclear magnetic resonance spectroscopy, and mass spectrometry, which is not really spectroscopy, but we use that to determine the molecular weight or the molecular mass of a compound. So these things help us give us data to determine what structure is. And then we'll spend a lot of the remaining or the end part of this semester on reactivity. So we'll look at reactions in general. We'll review acid-base chemistry. And then we'll get into the two main mechanisms by which reactions occur in organic one, substitution and elimination. So here is that molecule of the lecture, AZT. It's also called zidovudine or retrovir, and it's sold by GSK, which is GlaxoSmithKline, and Pfizer. The therapeutic indication, so a doctor will prescribe this to a patient, a pharmacist will dispense the medication, is it's an antiretroviral treatment for HIV. And it was featured in this movie with Matthew McConaughey and Jared Leto, Dallas Buyers Club. And so this shows the impact of organic chemistry in society, and that this molecule, which is a synthetic molecule, it's made in a lab, it's formulated into these pills that patients with HIV/AIDS take to lead healthier, more productive, and longer lives. So what we're communicating here, these are names. So we all have names, and the name is that structure. This really long name, that's the formal scientific name that's generated from the International Union of Pure and Applied Chemistry Nomenclature Rules. But what we see in these three ways of communicating, this is a space-filling model that shows the space of each atom. Notice you can't really see the bonds. So for example, this OH group, that's that OH. That's a carbon, that's a carbon. You don't really see the bond between the carbon and the oxygen here. You know, they're stuck together, so you assume they're bonded. But here we're depicting it as a line. And this is a ball and stick model. So they're, communicating structure in different ways. Again, we'll use this sort of line with letters representing the elements, just because it's the easiest way of communicating in class. So what's important about AZT? Why are we starting with a complex molecule, the first lecture of organic chemistry? I want to read this quote by Richard Feynman, who is the Nobel laureate in physics in 1965, to put into perspective what we're going to do in this class. You can know the name of a bird in all the languages of the world, but when you're finished, you'll know absolutely nothing whatever about the bird. So let's look at the bird and see what it's doing. That's what counts. I learned very early the difference between knowing the name of something and knowing something. So we know the name, that's the structure. But let's ask more questions about this so that we can down the road understand why this collection of elements and bonds in this molecule has this biological activity that's dispensed in the form of a pill that people take and help them lead healthier lives. So we're going to start off with a series of questions, and again, we're just drilling down into learning more about the function of AZT. How many different color types of atoms do you see? So there's white, there's gray, there's red, there's blue. So our answer here is going to be 4. So white, gray, red, blue, and what those are depicting are different elements. And we know they're different because the bonding patterns are different. Using your knowledge of Lewis dot structures, what color corresponds to which element? So again, you're going to have to review some concepts from general chemistry in terms of how elements bond. We'll review that cursory over the next week or two. And again, that gets back to electron configurations and atomic orbitals. So we have C, H, N, and O. So looking at the molecule, carbon is going to be gray. So we can eliminate A and B. Hydrogen will be white. So just through that series of questions, we see that the answer is C. So carbon's gray, hydrogen's white, nitrogen's blue, oxygen's red. And in the next question, we'll figure out why that is. So which of the following answers best describes how many bonds each atom forms according to the Lewis dot convention? So carbon will form 4 bonds. So we can eliminate A and D. Hydrogen will form 1. So we eliminate C. So our answer is B. So we get 4, 1, 3, 0. And I'll state that this is the neutral bonding pattern. What does neutral mean? Sometimes the atoms in those functional groups will undergo reactions. Will they have an excess of an electron, electrons, a deficiency of electrons, or a single electron? So those situations, you can have negative charges, unpaired electrons called radicals, or positive charges. So anion, radical, or cation. And so we're typically just talking about the neutral bonding pattern. And if something isn't in its neutral pattern, then it's going to have one of these other situations. How many explicitly drawn hydrogen atoms do we see? So they're represented as H. So how many H's are there? So there's 1, 2. So our answer here is C. Given the structure of AZT, how many explicitly drawn nitrogen atoms? So the bolded blue N. So 1, 2, 3, 4, 5. Our answer here is D. We see 5. Given the structure of AZT, how many explicitly drawn oxygen atoms in bolded red do you see? 1, 2, 3, 4. Our answer is C. The carbon atoms are not explicitly drawn as the letter C. So again, from the periodic table, that's how carbon is represented as C, but they're still present. How many carbon atoms do you think are in this molecule? Again, organic chemistry is the study of carbon, but we see there are no explicitly drawn carbon atoms here. Really, that's meant for just a time element, so it's easier to represent carbon in a different way. And what I'll do is I'll just go through and highlight the carbon atoms, we'll count them, and then I'll explain sort of the rules of this convention. I'm going to start right here with this bond from H to O to this thing here. So that's a carbon. Then I'm going to move along down this way. So this is a carbon. This is a carbon, so we're at 3, 4, 5. We move up, there's a nitrogen. This is a carbon 6, 7, 8, 9, 10. So there's 10 carbon atoms. So if we're building up the molecular formula, there's 10 carbon atoms, C10. So how do you figure out where that is? So we'll start with a point. So there's a point, and let's draw a line from that point. And at the end of that, we'll draw another point, so we have 2 points. So really what that could represent in the drawing convention is a carbon bonded to a carbon. And so they're bonded by a single bond, which we remember is called a sigma bond. What about 3 carbons? So C, C, C. So now we have 2 sigma bonds. And the way we would represent that is a line, so that would be 2 carbons, and then another line. So 1, 2, 3 carbons. And this is one of the reasons why I put that hexagonal template interspersed throughout the slide deck, is to help you draw these sort of angles so that we know, that when the 2 lines meet at a vertex, that is a carbon. Because with 3 carbons, if you just drew a longer line, it's still ending in 2 points. You don't really know that there would be another carbon bonded in there. So thus far we've seen that, agreed that carbon has 4 bonds. There are 2 explicitly drawn hydrogen atoms. There's 10 carbon atoms. With that knowledge in hand, how many implicit, so not drawn, hydrogen atoms are there? So we have the 2 explicitly drawn ones there and there. One's bonded to O, one's bonded to N. And what we have to do is, apply these. We have to go to each of those identified carbons and then apply these questions. So if we're starting at this carbon right here, we can see that we have 2 bonds shown, sigma bond, sigma bond. And we know that carbon has to have 4 bonds. So we have 4 bonds required. We're showing 2. So that must mean that carbon has 2 hydrogens. If we draw them in, there they are. So now we have 4 bonds total. And in the drawing convention, H atoms on carbon are not typically shown. And again, the reason for that is just a time element. It's just assumed that they are. So the test is we're now going to go down to this carbon atom here. So we can count, we have 1, 2, 3 bonds, so 4 minus 3. That atom has 1 hydrogen. And we continue on doing that same sort of analysis. And I'll just write the number. So 2, 1, this would be 1, this would be 2, that would be 1. This carbon atom right here would be 1. This carbon atom, as I've shown in blue, is showing 4 explicit bonds. So 1, 2, double bond, then that one, so that's 4. So 4 minus 4, that equals 0 hydrogens. This carbon atom is showing 1 explicit bond, so that's 3. And the remaining carbon atoms here and here are all showing 4 explicit bonds, so no hydrogens. So what do we end up with? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So our answer is D. And again, the slide here, if we're drawing things, so we want to stay on these sort of angles. So there's 2 carbons. There's 3 carbons, 4 carbons. And if we want to build pathways off this, we could put a carbon there, a carbon there. Again, you want to be pretty strict with your drawing, because I think that's going to help you understand the concepts better in this class. And I definitely encourage you to do a lot of problems, write a lot of things down, either on your tablets or on your pen and paper spiral notebooks. Get your thoughts down so that you understand when you're reading these questions, all these steps you have to go through to get to the right response. So what is the molecular formula? So the molecular formula of AZT. And again, that's the collection of all the elements and how many of each type of element there are. So we said there was C10, so we can eliminate B, D. The 13s for A and C are the same. We said there were 5 nitrogens, so that's wrong. So C's out, and A is our correct answer. C10, H13, N5O4. So that's the molecular formula. And again, it's a way of communicating. There's a name, there's a molecular formula, there's a structure. We're communicating the same thing through those 3 different ways. Now we want to use that C10, H13, N5O4 and calculate the molecular weight of AZT using the atomic mass units from the periodic table as shown. And if we recall from general chemistry how to do that, let's just set up some columns. C, H, N, O. How many of each? The atomic masses of each. 12, 1, 14, 16, and then multiply. Oh, that's 13, not 130. So what do we have in our rightmost column? I think we're going to end up with 7. If we had the 3 and the 4, then we have what? 2 plus 1, 3, plus the 7, that's 10, plus the 6, that's 16. Carry the 1 up here, that's 267. So 267 grams per mole. What is the point of doing this? Again, this is grams per mole. This is a piece of information that corresponds to the molecular formula. And so we solve this problem by looking at the structure, determining this, taking the atomic masses from the periodic table to get that. But what if we were presented the data in a different way? What if you were given this number? Could you then go back and figure out this? And then from the molecular formula, could you propose a structure? So organic chemistry, the questions can get a little bit more in depth in the sense of how they're asked, how you're asked to solve them. And you have to be very flexible in your thinking patterns. So in the line drawing convention of representing molecules in organic chemistry, how many electrons are present in a single or sigma bond? So we're going to use that Greek small letter sigma to represent a bond. So that's a sigma bond. So each element of that bond is contributing 1 electron, so we get 2 total electrons in a bond. What about a double bond? So there's our sigma bond, but what about if we put another bond between them? That's called a pi bond. So overall, that's a double bond. So we're going to have 2 electrons plus 2 electrons. It's going to give us 4. While a carbon atom is a carbon atom, it can be classified differently according to the functional group it is present in. A functional group, I'll just typically write Fg, is a specific collection of elements with a unique bonding pattern. Given the molecule AZT, how many carbon atoms have 4 sigma bonds? So we're looking for carbon atoms that have 4 sigma bonds. And remember, we already figured out there's 10. So we have to do this for all 10, apply this test. We'll start here. In this carbon, we see 2 sigma bonds. Remember, we need to get to an octet, so that carbon has 2 implicit hydrogen bonds, and we know that hydrogen forms 1 bond. So the remaining bonds are sigma bonds to hydrogen. So that's going to be, we'll count that. And we go down to here. We see 1 sigma bond, 2 sigma bonds, 3 sigma bonds, and then the last has to be hydrogen. That's the 4th, so we'll count that. The next carbon, we have 1 sigma bond, 2 sigma bonds, 3, so the last is a sigma bond. We move over, we'll find that that matches as well, as does this one. So we're up to 5 already. We go up past the nitrogen to this carbon. We see a sigma bond, and then this extra bond, that's a pi bond. So already we can't count this. The last element is a hydrogen, and that's through a sigma bond. So that one doesn't count. We know that this carbon, it has a pi bond to the other one, so that can't count. This carbon is showing 1 bond, so it has three hydrogen bonds, so that will count. So let me just change these colors here. So these blue ones are not going to count. The remaining carbon atoms here and here will also not count because they have pi bonds. And so we have 4 that we have not counted as answering the question. So that's going to lead us to 6 C atoms with 4 sigma bonds. So our answer is C. Given the molecule AZT, how many pi bonds are present? So remember, we're looking for that situation where there's, the sigma bond and there's this extra line, that's the pi bond. And so we'll go ahead and highlight those where we see them. So there's carbon with two bonds, another carbon with 2, then these 2. And then don't lose sight of the fact of the nitrogens. There's pi bond and pi bond. So if we count the pi bonds up, we have 1, 2, 3, 4, and 5. So in that situation, it just so happens that the 2 nitrogens, there's a sigma bond, then there's this pi bond, and then there's this third line, that's another pi bond. So that's called a triple bond. So overall, our answer is going to be C, which is 5. So again, you can use these slides if you're printing them out. Grab your pencil, start drawing, making sure you're keeping your angles nice and clean. So fill in your hexagonal pattern so you can draw some nice structures so that you're thinking of these things in your mind in a nice, clear way. So I think the first lecture sort of ended at that point. We'll just go through this question here, and then we'll wrap up this first lecture. The second lecture has already been posted on the YouTube channel. Given the molecule AZT, how many rings are present? So let me just fill those in, and I'll explain in a little bit what a ring is. So here is a ring, and here is a ring. So the answer is 2. But how do we spot what a ring is? Let me draw a C5, so 5 carbons. So there's 2, 3, 4, 5. 1, 2, 3, 4, 5. So carbons 1 and 5 are terminal carbons. C2 to C4 are internal. And so they form a chain, and the chain is linear. So we call that an acyclic molecule. What about taking C1 and bonding it to C5? So if we took the terminal carbons C1 and C5, bonded them together, that would form a ring. And that ring would have 5 carbon atoms in it. So these are called cyclic compounds or ring compounds. And what is a way to think about that? Well, if you're standing on carbon 1 and you walk to carbon 2, then to 3, then to 4, then to 5, you can get back to carbon 1. So where you started is where you end up. Now you can't do that in an acyclic compound because you start on carbon 1, you go to 2, you go to 3, you go to 4, you go to 5, you're at the end point. You can't get back, you're not back at carbon 1. You'd have to retrace your path, but then you're not going in a ring. And so these are just more words of describing the structural features present in molecules, acyclic versus cyclic.